Isn't my art collection beautiful? Luckily, these keys keep out evil people trying to steal it. Like these keys can protect physical stuff, there are also virtual keys that can protect all of your personal data online. Well, few years from now, all of your virtual keys can be copied within seconds by quantum algorithm run by a quantum computer. But before we understand how this powerful quantum algorithm works, we need to introduce you to quantum mechanics and the concept of superposition. Imagine having a little friend, Augusto, living in a world where the only existing colors are green and blue. Now, imagine him waking up in the morning and picking a t-shirt from his wardrobe. If you were asked which color is that t-shirt, you would definitely answer that it's either green or blue. Sounds obvious, right? Surprisingly, this doesn't hold in the quantum description of the world. For a moment, visualize turning the colors off. The whole world is black and white, and no one even knows what blue or green is. Now, suppose that in Augusto's wardrobe there is only one t-shirt and he puts it on. You might wonder, is he now wearing the green t-shirt or the blue one? Well, the question doesn't even make sense, since the colors are not yet defined. Everything you know is that if we switch the colors on, the t-shirt will have some chance of appearing either green or blue. So, what is the simplest way to treat an unknown property of an object if you just know all the possible outcomes and not the property itself? Just consider them both, superpose them. In physics, we say that the t-shirt before the measurement is in a superposition, and we represent such a state as a 2D vector. By measuring its components, you get the probability of seeing green or blue after switching the colors on. Another way of representing such a superposition is to write a sum of the possible results in these symbols, the ket symbols. So, do we have two colors at the same time? No. The t-shirt is just one, and its color is described by one single vector, just one. If you measure it, you will then have some chance to find it green or blue. Treating physical properties as superpositions is like thinking in multiple ways at the same time. Quantum computers are machines able to do so, and by using them, copying all of your data will be just one application of many. Let's see how it works and ask real quantum experts.
I'm Sieglinde Fendler. I'm responsible for the IBM Quantum Researchers Program. Right now we're in Germany. We're sitting in a little village called Ehningen, which is on the outskirts of Stuttgart. And we're right in front of the first commercial quantum computer that IBM has built outside of the US. And it's in collaboration with Fraunhofer.
Yeah, so my name is Christian Tutschke. I'm from the Fraunhofer Institute and currently head of the team quantum computing at the Fraunhofer IO.
So this is a very beautiful quantum computer. It's made with parts from all over the world. For example, the cooling system comes from Finland. The glass case that's around it comes from Italy, and even some of the electronics has been designed here locally in Germany. It contains a 27-qubit chip called the Falcon, and at the bottom of inside of this metal cylinder, right at the tip, it's operating around 15 millikelvin, which is colder than outer space.
Any field you can think of has a certain application for quantum computing. It was motivated by Richard Feynman back in the 80s for quantum simulation. Since these quantum systems, they rely on quantum physics, you can use a quantum computer inherently to simulate these systems.
IBM quantum computers are used for a whole range of research, from fundamental research to try to understand exactly how the qubits work and improve how they work, to various types of models and attempts at new predictions on chemistry problems, on financial prediction problems, logistics, optimization, and also different applications of machine learning.
To be honest, so one of the most important fields currently is the IT security. Why is this? It relies on the so-called RSA encryption, and RSA works like it's easy to multiplicate two numbers. 3 times 5, it's 15, but it's hard to say decouple this or to do this vice versa. 15 is 3 times 5. This is a difficult task. That's what Shor's algorithm relies on to find these numbers, these prime factors, and this is an exponential speed up with respect to classical computation, classical algorithms. Yeah, and that's why a quantum computer is very powerful in the IT security area.
Now, let's take a closer look at Shor's algorithm, which was named after Peter Williston Shor, who came up with it in the 90s. We know that this procedure lets us find the factors p and q of a large number n. For this, there is first a classical part which reformulates the factorization problem and can be solved on a classical computer. Then follows the quantum mechanical part, which can efficiently solve the reformulated problem. But before we get to that, let's start with the classical part first. Imagine a large number n consisting of two unknown prime factors p and q. We want to find these two factors, which becomes very difficult for large numbers. For example, take a look at this huge number. You can probably imagine that your laptop will need quite some time to calculate these two prime factors. But in reality, the numbers used to secure our data have almost 30 times as many digits. So we really need an efficient and clever way to calculate the problem. This clever way starts with guessing a random number g between 0 and n. Our goal for g is not to find a prime factor directly, but to be able to reformulate this problem. It is mathematically equivalent to our factorization problem to find an alpha which solves the following equation even if g was just a random guess. So, what is written here? We are searching for an alpha for which g to the power of alpha is 1 greater than a multiple of n. When we have found such an alpha, there is an easy way to find the prime factors p and q from our earlier problem, but we won't go into detail. Of course, we can try to calculate the fitting alpha with a classical computer, but on such a device, we are left with no choice but to try different guesses. This might take forever, and therefore, this does not seem like an efficient way to solve our problem. Exactly, this is why our internet is so secure. Now, let's see how a quantum computer can speed up our calculations. Our aim is again to find alpha. The wonderful thing about quantum computers is that it is possible to pass a superposition as an input. Do you remember this concept from Augusto's t-shirts? The input corresponds exactly to the superposition of Augusto's t-shirts from the introduction, but now with numbers, lots of numbers. To pass a superposition enables the computer to only do one calculation as opposed to calculating every alpha individually like in the classical part. This speeds up the calculation tremendously. In our case, the quantum computer uses an algorithm to calculate R1, R2, and so on for every ket in the superposition and stores the result in another entry. These R's are related to the concept of a remainder, but we will spare you the mathematical details. The important thing in this step is that you remember that the quantum computer only needs one calculation for the whole superposition. This new superposition contains more information than we might realize at first glance. We can make an interesting observation. If a number x has the remainder rx, then the number x plus alpha has also the remainder rx. Therefore, our superposition includes periodic information with period length alpha. When we draw the remainder rx of every number graphically, we get a signal which could look like this. Notice that it repeats itself with the period length of alpha. We can extract the period length out of our signal with a mathematical tool. Thanks to this, we finally found our alpha. With this, we can then solve our problem of finding the two prime factors p and q of n. The most important thing you should keep in mind is that a normal computer has to calculate every alpha individually, while a quantum computer can take a whole superposition as an input and find alpha with just one calculation. That's why a quantum computer is superior to a normal computer in terms of finding internet keys.
Okay, now we have learned how Shor's algorithm works in detail. We ask ourselves now, okay, is this now a threat? Should we be extremely afraid and should care about, okay, what comes next? Is everything unsecure? And the basic answer to this is no, we don't need to be. Why? Because quantum mechanics can be a threat in terms of Shor's algorithm, but it can also be a game changer to encode information differently. So use quantum mechanics to make the classical information more secure by using a quantum channel. And how does it work? Goes back to this BB84 algorithm, which we will see next.
How does this protocol work and how is that efficient? Augusto would like to send a coded message to his friend Beatrice through a public channel. For this, they both need to share a key using BB84. The key is a random combination of zeros and ones. In order to share the key, they will send each other photons, but let's stick with the t-shirt analogy. In such a case, we call the set of pure blue t-shirts and pure green ones a basis for all possible t-shirts. Of course, another basis can be built using another characteristic of t-shirts. For example, we can describe every t-shirt as a combination of a sleeved t-shirt and a sleeveless one. For each basis, Augusto and Beatrice need to agree on how they're going to represent each shape and color to a bit. This will enable Augusto to send his key using a sequence of those bases. They agree on a correlation table. Now, he can use that sequence to send his key to Beatrice in a secure way. Using only one basis would enable anyone to spy and have access to the key. But if Augusto had the choice between more than one basis, he could randomly choose between them by tossing a coin. For instance, if he gets heads, it means that he has a blue-green basis, else a sleeveless basis. The measurement of one property won't influence the other one. This implies that if he gets the basis that defines the color of the shirt, we'll have no information about the shape of it. It will be defined randomly. How is Beatrice going to get Augusto's key? Well, she will have to go through the exact same process by tossing a coin with the same choice of basis. Once she has her own sequence different from Augusto's, she's going to measure each t-shirt sent by Augusto. Thanks to her sequence, the measurement of each t-shirt will allow her to tell either a color or shape of it. Now, both of them have a key and they're going to compare the sequences of bases once again publicly. They're only going to keep the shared basis. Why? Because if Beatrice uses a different basis from Augusto's, she will get a random result. As a matter of fact, this way they will know which measurements of t-shirts are correct and which are false. Every step of this process happens without them sharing explicitly the results of Beatrice's measurements. Hang in tight here. You just need to keep in mind that the exchange of a key is a matter of choice of basis. You might wonder what's the goal of this protocol. Actually, this quantum protocol, as opposed to classical ones, enables us to tell if your data is being spied on. If you know you're being eavesdropped on, you can stop communicating. As we've seen, a quantum computer that uses Shor's algorithm could copy easily all of your keys, making them useless. But good thing that physicists came up with the idea of the BB84 protocol, because I think honestly, you wouldn't want people to spy on these weird pictures, right?